Hello and welcome to MicroLive. This week, in the second part of our look at word processing, what's on the market for the business user and how do you choose the right package?
Has the silicon chip had its day? We look at research which may lead to the optical computer.
And we go to Scotland to see a system for the fire brigade that has to work every time, no matter what the emergency.
Well, I don't suppose you'd fancy putting your home micro into here and sending it off at 240 miles an hour. But inside this dragster, there, if I can get at it, there is a computer. There it is, and it's used for monitoring the machine's performance, the fuel flow and the wheel and clutch slip. Now, this kind of control application is way beyond the scope of the home micro. For one thing, it's a hostile environment. But more to the point, a lot of the micro would be wasted. You don't need a monitor, of course, and you don't need the disk drive. You don't even need the keyboard. And many of the functions of the main circuit board become redundant too, the sound and the video chips, for example. But add some smart new chips and a lot of interfacing, and you end up with something like this. This board is the brains behind the car's brawn. It's being developed to control various functions on the car, and eventually it's planned to use one in a vehicle like this. It'll be used in an attempt on the world's wheel-driven land speed record, which currently stands at 409 miles an hour. The board is called Scorpion, and it was designed by Peter Miller. Peter, welcome. What can it do?
Well, it's a general-purpose control computer. It has a microprocessor. It has 24K of RAM in those chips, with battery backup, which also keeps the clock and calendar running. There's a 32K language in there, and numerous interface ports.
By interfaces, those are what you call inputs and outputs.
That's
is that
right, yes.
Now, inputs, in plain terms, are sensors, are they? Ways in which the board can learn about the outside
That's
world.
right.
What sort of things?
Well, we've got digital sensors like the switch. There are analog sensors like this temperature probe. And this device can measure the speed of rotation of a shaft, the direction of rotation, and also the absolute position of the shaft.
Presumably there's something very much like that on the car.
Yes, so there are a number of those, monitoring different functions. And also, one can drive this small camera. It's a solid-state camera, 256 1:8 resolution, and it plugs straight into the control card.
That is an input.
That's right. Yeah.
That's quite sophisticated for a small board.
It's not what you expect on a card of this size.
Those then are the inputs. What about outputs? What can it drive?
Well, again, you've got a variety of devices. There are various motors, DC motor, stepper motor, servo motor, even a Lego motor, and valves, relays.
Or if you really want to get complicated, we've even got a robot arm.
Well, this is a robot construction system. It's used in schools, and you can build it up in many different ways.
So we've got, what, 1, 2, 3, 4, 5 different motors there.
That's right.
Right, so those are inputs and outputs. We've got a very simple demonstration over here which uses much simpler inputs and outputs. This one is the input. It's a pressure pad, the sort of thing that you might get on a burglar alarm. And the output itself is just that light bulb there. But of course, between the input and the output comes the decision-making, the program. What kind of language have you used?
Well, a lot of control languages use the fourth approach, and I gather last week that was described as a write-only language.
A write-only language, yes.
Well, ours is definitely read-write, and it's based on more on Logo Pascal approach.
Can we see some code?
Got a routine called light, which is defined like this. It's a routine called light. It forever goes round this loop, which checks input 6.
That's the mat.
That's
yes.
right, for a condition, and turns the light on or turns the light off, depending on the result.
So the 4 is output channel 4,
That's right.
The light itself. I see. Well, that looks very easy to understand, and let's test it out. Sure enough, if I push on here, does it work? It does. It truly does. But that's a fairly trivial kind of application, isn't it? You don't even need a micro for that. Have you got anything a bit more realistic?
Yes, I mean, a program we've made up of many routines like this. We've got a slightly more complicated routine in this one, called door. The routine door goes round the loop forever. Repeating 4 times, it gets a key from the keypad, and it checks each one for being in the sequence 1, 4, 16, 13.
So this is a password, a code?
That's right, that's a password to get in. If at any stage you get it wrong, it throws wrong, which takes you back to the beginning. Otherwise, it gets to the stage of opening 7, waiting for a second, and then closing 7.
What at vast expense. We've provided you with a door. Perhaps you could pull that across and show us how it
well,
works.
this door is connected to port 7, and if I don't know the password, I can type away and nothing happens. But if I go around the keys in the correct order, hey presto.
Magic. And of course, at the same time, the light is still working. So this is a true multitasking language.
Yes, it's a multitasking language. You can run virtually any number of tasks. You can get hundreds of tasks, although the processor time will be shared between them, so that it will go quite slowly if you did have that many tasks running.
But why are we using a BBC Micro here? I thought this was a self-contained unit.
Well, the BBC Micro is a convenient keyboard and screen. It connects to the controller over a serial interface. You can use any computer in place of the BBC, and now we've programmed it, we can actually turn the BBC computer off. And things still continue to run.
Yes. Yes, and the light still works. So who's using these?
Well, it's used in schools, colleges, laboratories, industry, all over the place. And it's also finding its way into specialist applications, specialist products. We've got one behind us, actually. If you were wanting to do an audio-visual presentation, you might have something like this. You'd have some slide projectors, you'd have a sound, you'd have the lighting to control, possibly a screen to bring down.
That's a great deal to look after if you're also reading a script, if you're also looking at your notes.
That's right. So this unit here tries to simplify it.
So if I just press the start, it will all happen, I take it automatically?
That's right.
See, the lights should
lights
go
coming
down.
down.
Yes, they do.
The
Sound starts up. And the slide start. Now, those are, of course, outputs. What about inputs? Are there any in this application?
Well, there's a certain amount of feedback provided. There will be feedback with an electric screen about whether the screen's down or up, whether various devices are connected or not. And also, of course, there's the input from your pressing the keys on the keyboard.
Right. Thank you, Peter. Thank you. A very versatile unit. Many thanks.
Thank you very much.
Well, if you'd like to find out more about Scorpion, the details are in our notes. The Strathclyde region covers 5,500 square miles of wood, field and isolated islands. It's a fire brigade's nightmare.
Fire brigade.
There's a fire at Hartfield.
The control room of the Strathclyde Fire Brigade houses the most advanced computer call-out system in Britain. It handles all fire calls immediately, working out how to get the right equipment to the right location without error.
There's a fire at Hartfield.
Yes, what's the address?
Hartfield.
Hartfield. H-U-R-T.
Yes, hurry up.
In the heat of the moment, place names are easily misunderstood and slightly misspelt. But if the computer cannot match the name, it's programmed to find all the nearest alternatives.
What town is that in?
Eldersley.
The operator can then work out which is the correct name by its location.
Could this be Hartfield Farm? H-A-R-T. Hartfield Farm, Eldersley.
Yes, that's right.
It is. The fire brigade will attend. Thank you.
When the operator is satisfied that the name is correct, the computer is asked to select the nearest fire engines available. If the operator then accepts this advice, the system is told to go ahead. Details of the fire are transmitted down a line to the selected fire station.
The crew at the fire station now obtains a printed message giving them the details of the incident that they have to attend to. That has advantages in that previously a person would be involved receiving that information over a telephone and would perhaps be the only person at that moment in time with knowledge of the nature of the call-out.
Freezing fire, lads. Quick mobile to incident.
The computer is told that the engine's on its way by this button box, operated by the crew from the cab. Each key press sends a coded radio signal back to base. The firemen do this every time they move between zones on the fire station's map. This end of the system relies on one of the older microprocessors still in production, the Z80. Not exactly state-of-the-art, but the important thing is to use proven technology where lives may be at stake.
due course, one can envisage many fire brigades having printers in their appliances, and this would enable the control operator to send ongoing and updating information during an incident, and again, the fireground crews would have more pertinent, legible information, are less concerned about garbled or clash speech on an open channel radio.
Even though the system is still rudimentary, it gives clearly understood information, and the brigade say it's already cut the time it takes to alert a station in half.
Amazingly, if you report a fire in London, there is still no computer ready to work out which fire engine to send. As in London, they have to use operators leafing through a card index of available fire equipment. This is because, although the London Fire Brigade commissioned a computer call-out system from computer manufacturers Marconi 3 years ago, Marconi still cannot get their system to work. Last week, in secret factory tests, Marconi found that their system took all of 10 seconds every time it updated a new screen of information. On the Strathclyde system, this vital updating is immediate. The London Fire Brigade already has a brand new control room in place, but unfortunately no reliable system to plug it into.
This week, a piece of software called Mini Office 2 reached #1 in the software charts, and it's not even a Zappo game. It's available for many popular micros, and people are buying it because you get a spreadsheet, a database, communications, and a word processor, all for about £17. But now, at the other end of the market, Lesley continues our look at word processing with some business systems.
Well, word processors started appearing in the office and typing pools about 10 years ago. Today in Britain, there are about 100,000 of them in use. Now, with a word processor, one operator can do the work of 3 or 4 typists. A dedicated word processor, like this one from Wang, which is fairly typical, is a computer that's designed specifically for the task of word processing. Now, a system like this will cost anything from around £6,000. So, Elaine, what sort of thing is the businessman going to get for his money?
Well, this is a true multi-user system. Currently, you can have up to 192 users on the system, on one system, and then you can network those systems together. We at Wang, in fact, use 853 systems networked worldwide. But for the small businessman, his investment is protected for his workstations and printers, and if he wishes to add more workstations to the systems, it only costs him £1,600.
So he'd have no redundant machines as he enlarged up.
That's right.
But what about small businesses, us, the ordinary users, who haven't probably got £6,000 to spend on this sort of equipment? Well, last year, Amstrad launched this, a complete word processing package for less than £400. And that price and the sort of all-in-one box approach made many people consider buying a word processor for the very first time. Well, I've been joined by Lynn McTaggart, the editor of Which Computer magazine. Hello, Lynn.
Hello, Lesley.
Now, I believe you've just done a sort of expose of word processing packages, which is due out next month. So, shall we start by, can you tell me how you rated the old Amstrad?
We considered it a good buy, but not if you're using a word processor constantly. For one thing, the screen is kind of hard on your eyes. And also, it's a little plasticky, and we're not sure how durable it'll be over long-term use. Also, at that kind of price, you can't really expect after-sales support. But after all, at £399, you get a printer, a computer, and software. So, I mean, really, you could throw it away after a year or two.
Sort of dispensable, isn't it?
Yes.
Yeah, but I mean, having said that, computer's the operative word, because the Amstrad actually is just that. It's a computer, cleverly marketed as a word processor. But now, with all personal computers running word processing packages, and with there being so many of these packages on the market, I don't know where to start. I mean, how would I choose, for me, the right package?
It all depends on what you need it for. Broadly speaking, word processors sort of fall into 3 categories. There's those for secretaries who are doing copy typing and need to make things look pretty. And there's ones for writers who need word processors to create words. And then there are word processors for people who haven't used them very much, managers, people like that. And it all, you know, it really depends on what you need it for.
Right. OK, well, let's say I'm a secretary. In which direction would you point me?
I guess millions of secretaries really were brought up on WordStar.
Yes, I tried being brought up on WordStar this afternoon. I find it very tricky to get the hang of. For a start, you've got this help menu, which takes up half of the screen. I really would like to get rid of it, but I daren't, because I need it to remind me of which keys to press to get the commands to work. For instance, a simple command like delete, well, you have to do Control-G, that's for delete a character. Delete a word, Control-T, delete a line, Control Y. That all seems fairly simple, but of course, sometimes you've got as many as 3 key presses for one command, and if you multiply that by the hundreds of commands there are on WordStar, you've got so much to remember. I don't know why it's so popular.
It's popular because it's really the granddaddy of word processing. So many people have learned it that once you spend 3 months going through it, you don't want to spend that amount of time on something new. The other thing is it was written by programmers without really speaking to business people about how they think and work.
Yeah. But presumably once you have got it under your belt, I would guess that it's very flexible and possibly easy to use.
Well, it's one of those things that's good for making documents pretty.
Yeah.
It's very good if you need repetitive tasks done, like mail shots, and it's particularly good for setting up screens. So ideally, this kind of package is good for a secretary.
Right. To be fair to the people who make WordStar, they've now got WordStar 2000. That's their new package, and that is supposed to be easier to learn how to use.
Yes.
Well, now we come to people who maybe only use their word processing facilities once a month, even once a week. Even in that short time, it's terribly easy to forget the right commands. And that's why Apple have tried a different approach by making the whole system really simple to use. And this system, it really is simple. For a start, you've got a mouse. Let me show you how you sort of manipulate the text around. This is at the moment centre justified. Supposing I want to change that and to try it, see how the layout looks justified to the left. No, it's a mess. It's all ragged at the edge. So easy as anything. Pull down menu, go back to centre justify. It changes. Supposing I don't like the font, perhaps I might want something a little bit more grand than that. Then all I do is highlight the text that I want to change. Come on, highlight. That's it. Highlight it right through, that's it. And then select the font menu. I'll go for Venetian, because that sounds really grand. That's it. Oh, look at that. Well, that's very attractive. And you see, I didn't even touch the keyboard at all. That is a piece of cake. Who's it aimed at?
This is for managers and professionals who really aren't used to a keyboard. And it's for very simple inputting of text for things like notes and, the results of telephone conversations.
Yeah. I would imagine, though, if you were fairly dexterous on the keyboard, and once you've got the hang of it, then this would become very cumbersome, having to change back all the time.
Well, that's the ironic thing of it, Lesley. Things that are easy to learn are not necessarily easy to use.
And vice versa.
Yes, exactly. If you're a touch typist, you might find it cumbersome to let go of the keyboard in order to move that mouse around.
Well, fortunately, with this system, you can transfer the command back to the keyboard, which is a good thing.
Yes.
Right, now let's come on to people who are going to earn their living by writing, like yourself, like authors and journalists and things. What would you recommend for them?
Which computer says that things like WordPerfect and Samna are very good for writers because they're mainly built to handle long documents. They're also very good at reorganizing and revising text, things like editing and changing words. And they have all sorts of sort of add-on goody crutches for writers, like spelling checkers and word counts and things like thesauruses.
Ah, now that one interests me because I've never seen a thesaurus on a computer before, so I want to try. Well, a little bit of text, a sort of bogus letter. Ah, right, and the cursor is right on the word powerful, and powerful is a word that we are always using, and we're always being asked to find another word for it. So let's see what the thesaurus gives us. Well, first of all, I'll tell the system that I want to replace that word. We could replace it with, how about puissant? Puissant software? Stalwart, robust, hardy, I think strong is wonderfully imaginative. And look at that, it changes in the text immediately. Actually, that just goes to show why we use powerful. It's because it's the right word. What would the system like this cost me?
About £400 to £500 right now.
Does that mean it's going down?
Yeah, as the price of the PC drops, so does the price of software. And in fact, we just reviewed a package this month that's a £100 copycat version of WordStar.
Right. Now, we've looked at a whole range here. We've gone right from the top end, we've got the £6,000 worth of Wang, right the way through down to the £400 worth of Amstrad. How does somebody start to make a choice? What should their priorities be, really, do you think?
Well, it's really what you need first before how much it costs. Consider whether the person is going to be using it to make documents pretty, to actually create words, or just for notes, and someone who isn't used to the keyboard. Then worry about the price. Yeah. And also work around, use the word processor, tinker around with it a bit to see if those commands make sense to you.
Right. So if the logic fits you.
Yes.
Right. Thanks, Lynn, very much.
Thank you.
Now, of course, once you've written your masterpiece, the next stage is to get it onto paper, and that can mean much more than just printing it out. Later in the series, we'll be looking at the whole subject of so-called desktop publishing.
The microprocessor has been made possible by integrated circuit technology, which can now cram hundreds of thousands of electronic components onto ever smaller pieces of silicon. Now, the microprocessor is an immensely complex piece of electronic design, but behind that complexity is a very simple principle. The basic building blocks required to make any modern computer are always the same, and those building blocks are no more than simple decision makers or electronic gates. This AND gate, for example, has just two inputs here and here, and one output. Now, each of these inputs and outputs can be in one of two states. Either the lights are on or off. The state of the output here depends on both of these inputs being high, in other words, the lights being on. So this will be on only if that and that are on. In other words, it's an AND gate. One alone is not enough, both together will light the output. When simple gates like this are connected together in very large numbers, you can start to build up the very complex functions you expect from, say, a modern microprocessor. Now, a microprocessor is small, it's very cheap, reliable, and it's fast. But for an increasing number of applications, it's proving to be just not fast enough. Artificial intelligence work, Star Wars research, visual recognition systems are all making demands which the modern microprocessor and the modern computer will find it impossible to meet. Now, the problem is a fundamental one, and it's because all computers are built from electronics.
It's not possible in electronics to communicate information from one switch to another infinitely quickly. The reason for this is that they are circuits, and the speed of transfer of information in these circuits doesn't get smaller as the circuits get smaller. So that even if you make extremely fast transistors, you may be unable to transfer the information to the next one as quickly as they can switch.
So, as far as speed goes, electronics is a dead end.
In the end, electronics will reach a limit. It'll reach a communications brick wall, in fact.
So, what's the answer?
Well, the solution, we think, may lie in optics.
So here at Heriot-Watt University near Edinburgh, they've been working on what some people rather inaccurately call the world's first optical computer. Using a large industrial laser and a maze of lenses, prisms, filters and holograms, Desmond Smith and his team have reached an early landmark in what promises to be an important new technology.
We have to reinvent the triode valve from 1907. Essentially what the triode valve did was provide a means by which electricity could control electricity and thus provide a very fast switch with no moving parts. And that, of course, is the basis of electronics, later transferred to solid-state electronics in transistors and then integrated circuits. So we've had to essentially create an optical transistor. That's to say, a small device in which a quite weak light beam, albeit these days from a laser, can actually control another light beam and give exactly the same effect that the triode valve gave. That is, an all-optical switch plus the other attribute of the triode, which is gain.
Well, the switch in this case is this tiny optical filter, but it's one with very unusual properties. We're firing a laser beam down here through the filter, and I can control the intensity of the beam just here. Now, as I increase the intensity, you'll notice there's very little increase in the output here, until, that is, I reach a critical stage when suddenly, there you are, it leaps high. Well, that's our high output, our high state, and you'll notice that the system acts as if it's got a memory, because as I pull back the intensity, it stays high until I reach another critical point and down it goes. Well, that's with me controlling the beam, but I can use light to control it. We've got a second laser coming in just here, and just flicking that in as a trigger switch will switch the output high. There it goes. Now that is very much the way a transistor works, except that with a transistor you've got electricity controlling electricity. Here you've got light controlling light.
I haven't yet explained why we think that light can actually, in the end, produce some advantages over electronics. And the reason for this is that we can use the parallelism which is natural in optics. A lens, which we've got in our eyes, and when we look at each other, can resolve at least 1 million spots. If one has small devices in which light can control light, then this lens can effectively constitute 1 million wires. And that wiring possibility, in parallel, is what gives us new possibilities for computer architecture. And if we are able to do optical switches only at the same speed as electronic switches, but multiply them by a very large amount of parallelism, might be 10,000 or 1,000,000 times, then the overall speed of processing information could indeed be very high.
Try crossing two tracks on a printed circuit board and you've got a short circuit. But you can safely cross two or more beams of light and they won't interfere with each other. Now the upshot of this is you can split a single beam into many thousands of separate parts, doesn't matter if they cross, and each of them can be processed separately. Here, a hologram splits a single beam into 25 parallel beams, and each is being controlled independently. Which may not look impressive, but it is a form of parallel processing, and that's what the research here is all about.
But with the massive parallelism that's possible, the overall data processing rate could be very high. And now you can see how it might work, simply by comparing what might happen in an optical computing device with pattern recognition or image recognition using the eyes, where we've got a device that only works in about 10 milliseconds in the neural networks, but the eye is communicating at least 10,000 channels. And so even with that slow process, working with the computer that's the neural networks, we're able to recognize each other vastly more quickly than an electronic computer could possibly do. In fact, it couldn't even do the job at all.
So far, the most complicated circuit they've achieved is this: 3 separate switches that operate one after another.
We've been able to make, therefore, the first optical circuits. One device will drive another, and then a third, and then back again to the first. That is essentially a very, very primitive computational loop. Running it round the loop, we've been able to show that, in fact, optical logic can go round without error. And that's extremely important because it was that step in electronics, when we went to digital electronics round about the beginning of the 70s, that led, of course, to the accuracy that existing familiar computers have today. And we had to prove that that same step could be made in optics.
Well, it's taken 80 years to develop electronic computers. Will it take another 80 to develop optical ones?
Well, I don't think it'll take 80 years. I think we shall see some devices within 10 years, but I don't think we shall see a general-purpose computer within 10 years. Rather, we shall see something for some special purposes. For example, if you want to do pattern recognition, what you would like to do is to access a series of memories, not one part at a time, as conventional computing does, but in parallel, so that you could actually compare a whole series of patterns to the one you're trying to recognize very quickly. It is that sort of thing that we may see a specialized device somewhere in the middle of an electronic device within the next 10 years.
Professor Desmond Smith. Well, that's it for this week's programme. We're not on the air next Friday, but we will be back in 2 weeks' time with a disturbing story about computer security which could affect everybody. But until then, good night.